Today we're going to start looking at Newton's laws of motion and also to look at little devices that are helpful called free body diagrams. To start with, a force is either a pull or a push. Forces are what cause things to change their motion, change the direction they're going in, and when we study in physics how things move about and why they move about, we call that area of study dynamics. This video is intended to introduce you to the materials that we are going to assemble into an understanding of how things move. And so there are a couple definitions that we need to look at, then we'll look at the rules themselves. Mass. The mass of an object is simply how much matter, material, how many atoms it has in it. It's the amount of substance that goes into putting it together. It is completely different from the weight of an object. A weight of an object is simply how hard gravity pulls on it, and gravity can change drastically from place to place, but mass never changes. Next concept is inertia, and that's the tendency of an object to continue in its state of motion. So if something is standing still, it'll continue to stand still, and if something's already moving, it will want to remain moving in the same fashion. When we are talking about the push or the pull, that is a force, we're talking about a vector. It has magnitude and it has direction. And the symbol for it will be a capital F, and you can see the, oops, no you can't. And now you can see here's F, and there is the little vector symbol over the top of it. The unit for force is the Newton. The Newton is named after Sir Isaac Newton, who discovered these laws. The capital N is the abbreviation for newtons, and you can see there the units for newtons. A lot more about that later, but you can just notice that for now. Here are a couple of examples of vector forces. So you might push something 20 pounds to the right. You have both a magnitude and direction. You could push with a force of 115 newtons and go at an angle of 45 degrees to the south. So each one of these different things would be just an example of both a magnitude and a direction. Most of what we are about to study is going to depend on whether or not forces are balanced or unbalanced. So balanced forces, you can see here that all the different forces would add up. Let me restate that. That the imbalanced forces, all the opposing forces, would all add up to zero. For instance, if we had a person pushing in one direction and another person pushing with the same force in the exact opposite direction, they would cancel each other out, and there would be no movement or no change in the movement of the object. Whereas if you have an unbalanced force, you push on the grocery cart and there's not much friction on the wheels and nobody's pushing back in the other direction, then the little bit of friction from the wheels is not equal to your push on the cart, and they do not cancel each other out, and you'll end up accelerating your grocery cart down the aisle because you will have a change in speed or direction when there is an unbalanced force. Here are some examples of balanced and unbalanced forces. The two cartoon men here pushing on the orange box. If they are pushing with an equal amount of force, the box is not going anywhere regardless of how long they might push it. And then below that we've got a rugby scrum. You've got a lot of people pushing in one direction, a lot of people pushing back in the other direction. If they exactly balance each other, even though there are lots of different forces on each side, all of those balance with the ones going in the opposite direction, and there's no movement. However, if you have unbalanced forces, as on the right here, that these two men pushing that large blue box, assuming that there's not enough friction to keep them from moving at all, that they will be able to push, nobody is pushing back against them, and they'll be able to accelerate that large box. Another example might be the tug of war here. You've got three people on each side, but the three people on the left have pulled harder than the three people on the right, and as a result, the entire set of both teams falls off to the left because there's an unbalanced force to the left. Sir Isaac Newton, who lived from 1643 to 1727, was a brilliant man. He was involved in everything from mathematics to theology, and he is considered by many to be the most influential scientist that has ever lived. He was so smart that he invented calculus simply to help him do his own physics problems. And he is the individual after whom the unit for force is named, the Newton. And there are three basic laws of motion that we are going to learn from his studies. The first of Newton's laws of motion is the law of inertia. An object that is at rest will stay at rest until an outside force acts on it, an outside unbalanced force, that is. And a moving object will continue to move the same way it has been moving until an unbalanced force acts on it. So on the left here you see a large rock, and that rock has probably been sitting there for quite some time, and it will continue to sit there for quite some time until a net outside force acts on it to make it move. If you are in a car and it's already moving, as in this car on the right, it's going to keep on moving until an outside force acts upon it. And common experience is if you let off the gas, your car will come to a stop and not continue at the same speed, but it has been acted on by an outside force of friction, both where the car touches the pavement and also air resistance as the car pushes itself through the atmosphere. Newton's second law of motion is F equals m times a, and this stands for that the force, the net force, the unbalanced force, is always going to be equal to the mass of an object times how fast the object is going to accelerate. So if there's no net force, you would have 0 here for no net force, and you would have to have some sort of mass, so we'll just say 2 kilograms, if I can draw that here, 2 kilograms, and we would see that if there's no net force, then the acceleration would have to be 0, or the equation would not be true. So the correct way to state the law is the acceleration of an object is directly proportional to the unbalanced force acting on it and inversely proportional to the mass of the object. So to state the second law of motion in non-physics terms, it means that the larger the force that you exert on an object, the faster it will accelerate. So it would be the same size object in two cases. You push on it lightly one time, it doesn't move, accelerate very fast. Push on it very hard the second time, and it will accelerate faster. And then the other portion of the law is that the larger the object is that you're exerting a force on, the smaller the acceleration will be. And here we're talking about the mass of the object, how much substance there is. So if you push, say with a force of 100 newtons on a very large object, it's not going to accelerate as much as if you pushed with the same force on a much smaller object. So here's a cartoon of the second law of motion. This orange and yellow man here is pushing on 2 carts. We can assume that there's the same amount of friction in the wheels on each cart, and each time you can see the vector here for his force that he's pushing with. The vector is in the same direction and it's the same magnitude, but on the right hand side that we've got twice the mass that we have on the left hand side. So all the other things being equal, the cart on the left is going to accelerate faster than the car on the right, because the cart on the right has a larger mass to accelerate than the cart on the left. Now, Newton's third law is that for every action that happens in the universe, there is an equal and opposite reaction. So if I push my hands together in front of my chest, that my left hand pushes on my right hand and my right hand pushes on my left hand, and if my hands together aren't moving anywhere, I've got equal and opposite reactions in that situation. There have to be 2 different objects involved to see this action-reaction pair. So here we see a gentleman exercising his rights under the third law of motion. He's leaning against the wall. Now, when you do that, you wouldn't usually think of the wall as pushing on you, even though your body is leaning against the wall and you are pushing on it. But consider this guy's position. If the wall wasn't pushing back on him, he'd fall on his back. And so there is an equal force being exerted on his back that is exactly the same size as the force of his body that is leaning against the wall. Now, this is the second part of this video, and these are called free body diagrams. They are going to be pictures that represent the forces acting on an object. They're useful in organizing problems so that you can figure out what is going on. In a free body diagram, instead of trying to draw the object that you're analyzing, you just start with a simple dot, and then you draw vectors from that dot showing all the different forces acting on the object. And if the forces show that they're balanced, then you will have a constant velocity. And if the forces add up so that there is an unbalanced force, you'll have an accelerating object. It's probably better just to take a look at a couple of these, and we'll do some examples in class. So here's an apple falling through the air. Gravity is pulling it down. So if gravity is pulling it down, we would show the vector for the force of gravity is making this apple go down, and that nothing is holding the apple up. There's no string on the top, nobody's holding it underneath, and it falls down. Someone has probably thought, oh yes, there's a force acting on this, that there is some friction from the air that would tend to slow the apple down, but in most cases in this course we will ignore friction due to air. It doesn't really help much. It just makes the problem a little more complicated mathematically if you have to consider air friction. Now, here's the apple, and over here, here's the free body diagram, and all you see is a big dot right here that has replaced the apple. This is probably because scientists are very poor at sketching, and then we attach the vector there to show that the weight is pulling down. You can take one look at that free body diagram, that FBD, and see there's an unbalanced force, so it ought to be accelerating, and that agrees with your common experience because you drop things all the time and they accelerate towards the floor. Now we'll do a quick free body diagram of an apple sitting on a table, and the table is represented here by the green surface here, and once again gravity, the force of gravity, is pulling the apple down, but because the apple is on the table, it's not headed down, it's not accelerating in that direction. And there is a force acting on the apple. Some of that doesn't show because of the red on the apple, but here's a vector showing a force exerted by the table on the apple. It's called a normal force. That's the normal force, and normally the table will hold the apple up if it's strong enough. So when I now reduce this to a free body diagram, such as this one right here, we see that we once again have the weight of the apple is pulling it down, but now we have the normal force exerted by the table to hold the apple up is in the exact opposite direction and the same magnitude, and so these two cancel each other out, and the net force would be 0. So it's 0 net, this is horrible, force. It's hard to write with a mouse. So 0 net force here. And we will do some more examples in class after this brief introduction. Thank you.